for what is lab experiment number 5 in Material Science 410, Spring 21, where we'll look at the fundamentals and ideas for this lab and for differential scanning calorimetry, DSC. So DSC gives us the tool needed to characterize the thermal property of polymers. As you may or may not know, polymers undergo a number of thermal transitions that correspond to increasing movement in the polymer side chains and backbone. And this has implications on properties such as stiffness or viscosity, and temperature allows us to transition between various states. So at the very low temperature condition, polymers are vitrified and rendered glassy, very stiff. Amorphous components in here, the sort of random loops you see here in this diagram, transition and start to move as we move across the glass transition temperature. So the glass transition temperature is associated with the amorphous materials present in a polymer. As you see here in this rubbery state, where polymers are less brittle, we still have some crystallites present, represented by the figures in here that have chevrons or what appear to be springs here, showing packed chains. Moving the temperature up past the rubbery plateau, a melt can occur where all crystallites melt and disorder, and now those packed arrangements are gone in our diagram. In another scenario, it is possible that the material we started with had not crystallized as much as possible. So once the rubbery plateau was achieved, these chains, which are now moving above the glass transition temperature, can access conformations that can allow for addition to existing crystallites or nucleate new ones, and further crystallization can occur. And we see this reflected in our diagram where more chevron type structures have evolved. Sometime thereafter, melting can occur, and that still happens at the exact same melt point. Okay, so possible thermal transitions that we see: glass transition temperature, melt transition temperature, crystallization, and not shown on the diagram, ultimate decomposition of the material can occur for most materials. We've seen here that the glass transition temperatures depend on the heating history, so that is the heating and cooling rate, to affect things like content of amorphous material and crystalline material. And not only that, but the heating and cooling rate, as well as the ultimate structure present in the macromolecule. Okay, so to define and help us understand that transition from the glassy to rubbery state, we have the glass transition temperature. So this is known for a polymer. It's the reversible transition from a hard, relatively brittle, glassy state into its viscous or rubbery state as the temperature is increased. The glass transition temperature turns out to be a characteristic that is unique to many polymers. So shown here is an inexhaustive list of many different synthetic polymers, where we see polyethylene, polypropylene, vinyl acetate, ethylene terephthalate, vinyl alcohol, PVC, polypropylene, polystyrene, like we have for our lab, and PMMA, listed with their TGs. And you can see the TGs vary from very low temperature, minus 125 C, to almost 105 C for the PMMA acrylate or plexiglass material. For us in this lab, we'll be looking at that of polystyrene and touching on some of the ideas of TG using some of the examples on this list and elsewhere. So, as we mentioned, below the TG, the polymer is glassy, stiff, hard, and non-flexible. And this is owing to the fact that there's restricted rotation in the polymer main chain, and the chains are somewhat rigid. Okay, so main chain is restricted against rotation motion. Above the glass transition temperature, we know that the volume increases and we start to access a more rubbery and flexible state, And this can only be had if there's internal rotations and movements that are allowed. And typically, many repeat units move in concert or in unison together, like the main segment of a snake as it moves across the floor. It's also known that all polymers have at least one TG. Some of those points are reflected in the graphs where we see how volume goes with temperature for materials. So coefficient of thermal expansion would establish the slope of the glassy state of a material. When this slope or the coefficient of thermal expansion takes on a new value, a new material is evolved and we have the rubbery state of the material, and the transition between these two modes is the glass transition temperature. Modulus, like Young's modulus versus temperature, is shown here, and so we expect material to be very stiff, a lot of force per unit area to distort the dimensions of the material, and that at some transition temperature called the TG, that it takes far less force per cross-sectional area to change the shape of the material, and we end up in the rubbery state in that case. Okay, and in the photograph before, we have polylactic acid below its TG. We see a cup not distorting under its own mass. And if we heat that above the glass transition temperature here, temperature is just above 60 degrees centigrade, the material flows under its own mass, moving towards a puddle-like state like you've experienced with liquids, for example. So some structural effects here that tune the glass transition temperature. So as we mentioned, it's the chain mobility, the main chain's ability to move, that are going to affect the TG. So conformational flexibility in the backbone of the polymer is how the TG is set. So size, or the steric bulk of side chains, is a major way to tune the TG of a polymer. Secondly, interactions between polymers are going to be able to restrict the motion of units of the main chain against modes that could lead to motion in unison for many repeat units. So for that example here, we see an example here where we have hydrogen bonds in the nylon, a polyamide, nylon 6,6. And these hydrogen bonds present here would impede many repeats in the main chain from moving and rotating to favor a TG. So hydrogen bonding here has increased the TG in this nylon 6,6. Okay, to touch on the steric influence that we just mentioned, here's another example. Here's polyethylene, showing about 5 repeat units here. And we show and report the glass transition for this material as 120 degrees C negative. By swapping out side chains from the smallest atom on the periodic table to one of the smallest carbon units that we can consider, we can see the implications on TG. TG changes from minus 120 and goes up by about 100 degrees to almost 100 to minus 15 C in this case. The larger methyl group is responsible for the influence on TG, given its steric hindrance on coordinated motion of main chain units in this polymer. Considering that even further, let's swap out that methyl group and go to an even larger, more sterically hindering phenyl group here for polystyrene. All other atoms and architecture are the same to polypropylene and not far off that of polyethylene. Here, the larger phenyl units are responsible for the jump in TG again, almost by 100 degrees C, all the way to 100 C for the polystyrene TG. Consider that further, swap those phenyl groups for something even bigger, and here as we consider something more kind of unique, the vinyl carbazole, where we've placed carbazole units for phenyl units, TG goes up by almost 200 degrees C. Clearly, the steric bulk of the side chains here is having a major influence on the glass transition temperature. Okay, earlier we touched on nylon 6,6 having hydrogen bonding, providing intermolecular forces between FON groups bearing a hydrogen and an FON element elsewhere. And this restricts motion in the main chain to provide a high TG. Dipole-dipole interactions can also provide that. So here we recognize oxygens as being electronegative, carbon as a consequence not as electronegative, gives us a dipole, and we would have another dipole across to another molecule. This dipole-dipole interaction is also significant and provides a reason for higher TG than otherwise. Removing those intermolecular forces, dipole-dipole, and hydrogen bonding, all that's left is London dispersion forces, where temporary fluctuations in the electron cloud in the molecule allow for subtle but still present intermolecular forces that are the weakest of the set, and that TG is very low. So to summarize, we've seen here that TG will increase with the presence of bulky pendant groups. If we can stiffen the backbone by installing sp2 units, things like double bonds, such as some cases in polybutadiene, polyisoprene can even have double bonds in the main chain. So those areas are stiffer than other derivatives without those double bonds, or even materials like polyphenylene sulfide, where phenyl groups provide those sp2 carbons to stiffen the main chain. Chain symmetry can help, so the less kind of random a side chain is positioned, the more symmetric it is, the more proximity a main chain can have to the next to build intermolecular forces and possibly crystallization. Polar groups for dipole-dipole bonding, and of course cross-linking that permanently bonds neighboring chains together will affect TG. TG will accordingly decrease with things that provide void space, like contaminants or plasticizers, to help provide some opportunity to move components of the main chain into that empty space near those contaminants and help allow the TG to occur at a lower temperature. Positioning flexible groups like CH2 or oxygen ether type units in a main chain can help as well. And even avoiding polar groups, so positioning a lot of non-polar groups in the main chain and providing structural disorder like atactic options can give us low TGs. How about melting? So melting is a process of distorting a crystalline feature in a polymer. So polymers can also undergo a melting transition. And what's important here to note is that this melting transition is always at a temperature that's higher than the TG. Okay, and so of course melting is the disruption of any crystallites present, and this can occur in polymers. In order for this to be detected, for example, there must be a significant crystalline component, or there must be regions here that are present, and it is possible for no melting transition to occur depending on the history of the sample. So amorphous polymers are those that cannot crystallize no matter what history you apply to the material. So you could heat, cool slowly, do all sorts of temperature variations. You would never be able to generate crystalline regions. And so there would never be a melt transition, but we would expect to find a TG, given that all the material is in the amorphous state. Crystalline or semi-crystalline polymers will definitely have the TG, as said earlier, and they may have a melt transition temperature dependent on the history. If the history has programmed To not allow for crystallization, most of the material will be in an amorphous state and very little melting can be detected. If the history is more routine or very much programmed to favor crystallization, there will be lots of crystallites to detect, and we will see a large signal for TM at the expense of a more muted TG signal. So that is to say, in semicrystalline polymers, that the amorphous material is in balance with the amount of crystalline material and vice versa. So, further in the polymer area, the melt transition rarely shows up as a sharp melt point like we see in small molecule cases, given the complexity and the macromolecular state of the sample, and melt ranges are common in the literature to be found. What we saw for trends in TG, how we could influence TG, largely extend to how we would expect it to evolve or tune the melt transition temperature. Things like steric hindrance of side chains, flexible groups in the main chain, and intermolecular forces between chains. So, differential scanning calorimetry is a technique that can determine TGs and TMs, and as well as crystallization temperatures. So here what a graph looks like is a report of heat flow, which is typically in milliwatts of power on a heater driving a temperature change on the specimen, often normalized for the amount of material present, say in milligrams. The x-axis is clearly going to be temperature to allow us to show these ultimate different thermal transition temperatures. Typically, an exothermic direction is indicated on the graph, where positive peaks indicate an exothermic process and negative peaks or wells indicate an endothermic process. So it's important for the user and the student graphing these plots to label which direction is endothermic or exothermic. Okay, so recalling that endothermic are transitions that require energy. This is going to be useful for breaking intermolecular forces. Breaking bonds requires energy. And exothermic processes are the opposite. If we can bring molecules together, form stronger bonds, we might release energy. This should fit with the ideas of crystallization and melting, for example. Other signals that can be found in a DSC curve are signals for cross-linking or Kehr. So here, an exotherm is shown as new permanent covalent bonds are made, and the symmetry and the profile of this can be very different than what we see on screen, but generally exothermic peaks are expected. And oxidation or degradation can be known here, and the sort of change here can be very different depending on oxidation or degradation events that are occurring. The glass transition temperature that we've talked about here is known as a step change in the profile here of the heat flow versus temperature for a polymer specimen. Okay, so notice that we've got from a higher value to a lower value when the exothermic direction is up, exo up. Okay, so here's an example for polyethylene terephthalate showing almost all of those features. Here's the zero mark. Okay, so all the data is largely below the x-axis here. Heat flow is indicating that we're applying heat into the material, so we are exo up. So we're heating the material, trying to get power on the heater to drive temperature changes at the specimen relative to an empty pan that is otherwise holding that same specimen. And as we ramp up temperature, we eventually go through a step change and we register the glass transition temperature for PET. This specimen had not yet fully crystallized, so once those amorphous components are able to move and rotate, they can acquire new conformational options that weren't there before, and they can crystallize further. So this specimen is not crystallized as much as it could, and we register a crystallization temperature, an exotherm, TC. Continuing to heat, we now stand and have the opportunity to melt crystals that were present even before that crystallization event, and those that we've generated during the scan. So all crystallites melt here at the melting endotherm, and we have a TM value of around 250 here versus the TC value of near 150. Okay. And for this scan, temperature ended before any oxidation or cross-linking was possible, and that completes this heat scan for this DSC scan. In practice, cooling curves can be generated by returning the sample from its hottest condition back towards the starting temperature condition, and many of these features will be found in that cooling curve as well. Lastly, so a heat and a cool profile are common, and often a final heating curve is applied to show a DSC heat curve that has erased much of the history that was present and influencing the data in the first heat curve. So a heat-cool-heat experiment is very common in polymer DSC. Okay, I think we've touched on all these main features, things like the TC, the TM, and the TG.